So yeah, with that, let me start presenting. I'll skip this slide. Thanks for the introduction again. Um, yeah, but one quick thing about myself. I think whatever I've shared, what I'm going to share, um, it's something that I've done in my previous team. Um, my recent focus is on building the infrastructure to support AI workloads, specifically LLM workloads in Azure. Um, all right. So um, Viva Insights is the product that we as a team built over the last 6-7 years in Microsoft. Um, it's not a very popular product, primarily because this product is not um, used by end customers like us. Rather, it's mostly used by organizations, um, big organizations specifically like Accenture, TCS, uh, Walmart, etc. Right? So, uh, and okay, so I'll briefly explain what this product is about and why I want to start uh, by explaining this product, because I think this is kind of a good segue into all the big data concepts and the challenges that I'll be explaining shortly. So, so this product, what it offers to customers is it basically analyzes all the collaboration that happens in within any specific organization, right? And when I say collaboration, um, when you send emails, when you schedule meetings, um, when you send a Teams message, or when you make a Teams call, we basically take all this collaboration data, right? And just to understand the scale that we are talking about, there are organizations where there are a few lakhs of employees, right? So, and we are talking about collecting all the collaboration data that's happening every second, every minute over a period of time, and and analyzing the collaboration pattern. So that's the product we have built, and of course we do all this with the consent of customers. In fact, customers pay us to do this analysis on behalf of them. And what does customer get? We produce various insights after mining this collaboration data. Um, uh, so we give insights about employee productivity, and we also give personalized recommendations to specific teams or individuals. In general, it's all about data-driven insights, right? For customers. So to give you some examples, what kind of insights we produce, right? So it could be as simple as, hey, how much time is spent on meetings, right, by each and every team in the organization, right? This is the most basic insight that we produce, right? And the reason why our customers are interested in is, especially given the hybrid work environment that we are all in, um, uh, the number of hours spent in meetings, in sharing information, communicating with peers has increased drastically, right? And that has significantly impacted the productivity of employees in the organization, right? So that's why organizations like, including Microsoft, are very interested in tracking how much time are people spending time in attending meetings, right? And it's not just attending meetings. It's about how effective the meeting is as well, right? So, uh, and the other insight could be how many of teams are working more during after our collaboration, right? Let's say if your organization regular work hours is 9 to 5, we track how many hours people work after their office hours, right? And this will influence the employee well-being. So these are all simple metrics. There are other complex metrics that we or insights that we produce for customers, right? So, for example, uh, we can identify which teams are not well connected with the rest of the organization, right? So that means this team is basically working on something, but they are not actively collaborating with the rest of the organization. This means the team might not know what's happening outside of their immediate team, right? They are basically cut off from what's happening with the rest of the organization, which is not good in long term, right? So it's important for every team to be connected with other teams, if not all the teams, at least some teams, um, so that information flows to each and every team in the organization, right? Now, um, how do we produce these insights? How do we mine these insights? So before that, any questions on this product that I've explained so far? Right. um, so so how do we do this? As I mentioned earlier, we basically collect all the collaboration signals from each and every employee in an organization, right? So we take the email collaboration, instant messages, meetings, and there are other mode of communications that we consider as well, which is not super critical for this presentation, though, right? Um, and after we collect all this, what do? We basically create a graph, right? Saying person X has spent this many hours in meetings with person Y, right? And person X has spent this many hours um, uh, chatting with the other person, right? So this is the collaboration. This is the graph that we generate, right? Basically, we are talking about a graph with um, lakhs of nodes and uh, and uh, several edges, right? Uh, and so it's you can imagine the amount of data that we had to uh, ingest, process uh, to create this graph, right? And after we create this graph, we uh, we run various algorithms, right? Um, uh, One of the popular algorithm that you might know is this page rank algorithm, right? So um, page rank algorithm is used by Google to rank their pages based on how popular the page is. We run the same algorithm with some modification um, on this graph, right, to determine um, uh, people who are well connected with the rest of the organization, right? The algorithm is the same, but the insight that we are able to mine using the same algorithm is totally different for our case, right? And we call these people influencers in our product. So we basically identify which team or which organization has highest number of influencers or lowest number of influencers, right? And then we show these insights to customers, right? Of course, we don't want to identify an individual as part of this analysis, because our end goal is to not to pinpoint a person saying whether this person is influencer or not. Rather, it's for the organization administration to know um, uh, people who are our team who do not have influencers, right? And see if they can take some action item to increase the number of influencers in their team or organization, right? So we always produce all these metrics not at an individual level. We in fact anonymize the person name, etc. We always aggregate these insights and show it at a team level or organization level, right? Um okay, so this is a typical data processing pipeline that anyone who wants to build, who wants to do big data analysis will go through, right? So these are the stages that are typically involved in big data processing. So first is the ingestion. In our case, we basically extract these collaboration signals from every user's or employee's mailbox, right? So all the collaboration that a person does in our organization will be stored in their own mailbox. We call it user shard. And so we are talking about extracting these signals from each and every user shard, right? And in fact, we have a process running in each of these users' mailbox, which periodically sends these signals, and then we store all these signals in blob storage, uh, which is a doc. Blob. I don't know whether all of you are familiar with blob store. It's a distributed key value store where you can save any data with a key, right? And then you can query or download the data using a key. So the data is first uploaded there, and then there's this ingestion pipeline which tracks all these data that's uploaded into the blob, and we so before we start the ingestion, we have to make sure that the data is fresh, data is not stale, and we have extracted all the data, or most of the data from all the mailboxes, because in the distributed systems, failures are bound to happen. So we have to account for it, but at the same time, we have to make sure that we have good quality data to produce the insights, right? So we have something called a completion tracker that tracks how many mailboxes are extracted, and once it crosses a threshold that says, hey, this threshold is good enough to consume this data and produce insights, the ingestion will start. So ingestion will basically copy all the data, collate all the data. It does some pre-processing, including data cleaning, data duplication, etc. And then we move on to the next stage, which is processing. This is where we and one more thing, as part of the ingestion, we have to make sure that uh, the format in which the data is finally outputted is optimal for processing, right? This is a key factor that we need to consider while ingestion. I'll talk more about this in the upcoming slides. So in processing, we basically take the data that's processed and outputted in a format that's optimal for processing. And we run big data jobs, right? So in our service, we use Apache Spark for all our big data processing. So we run multiple big data jobs, one after the other, um, and we produce the insights. And once the insights are produced, it's again stored in a blob store. And here also format matters. The format in which the data is outputted, it has to be optimal for the consumers, right? And then, so once this data is stored, now customers can, of course, we have our own dashboard which customer can come at any point in time and query this data. And customer can load this data in their own data visualization or data analysis tool like Power BI or Tableau, etc., to analyze this data. So that's the last part, which is analytics. So this is the typical data processing pipeline. Cool. Any questions on this?
Participants, if you have questions, you can raise your hands.
So I'd say here is where my presentation actually starts. What I want to share uh, in the session is basically all the challenges that we faced when doing big data processing as part of this product, when we build this product, right? So I would be using a notepad as well, just to um, um, share the structure in which we basically ingest the data, etc. So in case uh, if you don't see my screen, please tell me, um, so that I can fix. Okay, cool. Um, all right. So as I said, we have terabytes of data, sometimes petabytes of data that we have to process. Now, how do we handle the scale, right? Uh, so one option is we can scale up the machine, but a single machine can scale up only up to a certain point, uh, and there are limitations to it. Um, so the obvious answer is we scale out, right? We add more machines, uh, and that should solve the problem, right? Because more machine means more power, and we should be able to uh, process um, any amount of data, right? It doesn't matter whether it's terabytes, petabytes. We can always add more machines and scale out, right? Um, yeah, that's true. But there are some problems. Can anyone uh, share the problems that they faced uh, while scaling out the compute? Would be happy to know learnings from your side. Or
There are questions
to
in the chat box.
oh, I see. My bad. Um, yeah, cool. What is the storage medium? Do you use HDFS or some other facility? Amazon S3. So we use something like Amazon S3. Um, we in Azure we call it blob store, but it's essentially an equivalent of Amazon S3. That's where uh, we store all the data that's ingested um, uh, as part of the ingestion pipeline. In fact, that's the storage that we use for all the stages that I've explained, right? From ingestion to analytics. Although the format in which we store the data might vary in each and every stage, because the format we choose has to be optimal for the consumer, right? And in every stage, the consumer data is different. So we have to choose a data format accordingly. Did I answer your question, Ajay? Okay, so let me rephrase that question. Just because we add more missions, uh, for example, let's say with one mission, you get um, um, X as the efficiency, right? By adding 5 missions, can we expect 5x efficiency? Always, is it guaranteed? Okay, communication latency. That's great. That's true. Yeah, communication basically. Every mission has to interact with other missions, so there is a need for synchronization, right, at some point, right? And that boils down to doing or communicate every mission communicating with some or all the other missions. um, yeah, that's a good point. What else? network bandwidth is good. Yes. Yeah. The network is critical. In Yeah, but just because we have good network doesn't mean we can still achieve 5x the efficiency, right? Because yeah, if you have good network, yeah, that will nothing like it, right? But unfortunately, um, the network um, will have limitations, will have reliability issues, right? And um, so we cannot guarantee that network is good always, right? We can try to optimize the network, um, but even if the network is good, um, are there any other factors that uh, that can affect the performance, the efficiency that we get? Okay, sounds good. So this is what I'll be focusing on in the rest of the presentation. So what are the challenges, right, in just scaling out? So, okay, so the first challenge is um, in today's world, I think um, most of us want the storage and compute to be decoupled, right? So, as Ajay pointed out, if you go back maybe 10-15 years, um, in Hadoop world at least, the practice is you have a Hadoop cluster uh, running, and the same cluster is responsible for both compute and data storage, right? So, um, so that what that means is, uh, customer wants to do some analysis on their data. They first load the data to the Hadoop cluster. HDFS is the service um, that runs within the Hadoop cluster, which is responsible for um, persisting the data, right, in the cluster. So they first have to load the data into HDFS, and the same cluster also does the compute, right? So basically, the MapReduce job that we run in Hadoop. Sorry, I am using terms. I'm assuming that most of you will be familiar with MapReduce, but let me know if you have questions. So MapReduce is the paradigm. It is the most popular paradigm in big data world. I'll actually briefly describe about MapReduce in my later slides and the problems with this framework. But essentially, it's a big data um, uh, paradigm that's very popularly used to process data in a distributed fashion, right? So in Hadoop cluster, 10-15 years back, we first load the data into the Hadoop cluster, and then we use the same cluster to process the data. Of course, there are some advantages with this, right? One is the data is located in the same cluster where the data is getting processed. That means the latency in reading the data and writing the data is very low, right? It's much more efficient with this approach. But then the problem is, um, if you want to shut down the cluster, right? After you're you're done with the data processing, that means you lose the data, right? Uh, I think if I remember correctly, there are options given in the big data cluster to basically pause your cluster so that you don't lose the data. But essentially, the problem that we are trying to solve is, hey, how do I make sure that my data remains in my storage of choice, right? So that I don't have to copy the data every time I need to do data processing, but I can bring up a compute cluster whenever I want to do data processing and read the data from my own storage, do the analysis, and then store the data in my as per my storage of choice, right? So of course the obvious benefit with this is um, uh, you don't have to move around your data, copy the data just to do data processing, right? So you can store it in one place, and you can anytime you want to do data processing, you can bring up a compute cluster, do the analysis, and you can bring down the cluster so that you only pay when you want to do the data analysis, right? And you can immediately shut down the cluster once you're done with the data processing. So you save cost, uh, which is a big deal for organizations like us. Um, but then the downside is um, now uh, we had to pull the data into memory from a storage that is not co-located uh, with the compute cluster, right? Um, so what this means is the data might be present uh, uh, in USA, but I might have to um, create a compute cluster in a different geography and pull this data, right? So the downside is um, there's latency involved in reading the data. In fact, we are talking about um, multiple factor increase in latency, right? Compared to uh, storing data in HDFS that's co-located with the compute cluster. So, so that means the latency in reading the data has increased drastically, which is a very big thing because we are talking about reading terabytes or petabytes of data, right? And this will have severe impact in the performance of your overall job, right? So this is the first challenge. So I'll first explain all the challenges, and then I have a slide which talks about some of the solutions optimizations we have done to mitigate these challenges, right? If possible, solve these challenges. Cool. So I have more questions. Is Hadoop still used in storage of huge data and its processing? Um, Hadoop, I think that answer is partly yes. Uh, so Hadoop as a framework has multiple, has built multiple, they've built multiple components, right? Of course, the most widely used one is the MapReduce framework. Um, but as part of building Hadoop, they also had to build components like resource manager. There's a component called Yarn, which is a acronym. The full name is yet another resource manager. Uh, and the good thing is they built this component in such a way that it's not um, very specific to MapReduce paradigm. It can be used for any big data paradigm. In fact, we use Apache Spark um, with Yarn as the resource manager. So to answer your question, yes, Hadoop is still used, but not the MapReduce one, but the other components that were built with Hadoop, right? Especially Yarn. Okay, cool. So the second challenge that I want to talk about is the data shuffles, right? Um, so here is where I need to explain what MapReduce framework is. So let me briefly explain what MapReduce is, a framework does, and then I'll explain more about this challenge. Um, so let me use my notepad. Right. Okay. So in my previous slides, I briefly spoke about the Viva Insights product and how we analyze the data. So let me give you a very simple example. Your slide is not visible. Can you see my notepad?
Yes, it's visible.
Oh, okay, sounds good. Sounds good. Yeah, I'll switch to slide once I explain what I want to explain. Okay. Okay, so let's say there are, let me call employees, right? There are different employees in organization, right? Let's say employee one, uh, employee two. Um, yeah, let's start with two employees, and we extract um, all the mail collaborations, um, meeting collaborations, and the team chats calls, right? So let's start with the meeting. Okay, somebody is saying slides are not, oh yeah, slide is not visible, but can you see my notepad? And can you also hear me?
Yes, yes.
Okay, sounds good. Chandra, probably you might, I don't know, you can try reconnecting and see if that fixes the issue. Okay, so let's consider a signal called mail sent, right? So that means employee one, uh, let's call it E1, has sent an email to employee two, and or actually let's not consider, right? Let's call meeting, right? Let's say employee one attended a meeting, um, um, and as part of this meeting, um, there were three employees who were part of the meeting, E1, E2, E3. I'm calling employee one as C1, right? And yeah, employee two also attended this meeting, uh, where E1 and E3 were present, right? So this is how the signal, this is the signal that we extract from each employee's mailbox, right? So, and let's say there's a mail where employee one sent an email to um, employee two, employee four, right? And employee two sent an email from, yeah, he sent an email to employee one, uh, employee five, right? So let's consider these signals. So the processing we do is, and I want to explain how we leverage MapReduce framework, right? Um, so and so we are talking about distributed computing, right? So let's say distributed data processing, right? So let's say there are two nodes in the cluster which we can utilize to process this data, right? Um, Now let's say for node one, um, employee one's data is given, right? So node one uh, takes these two data, right? So how we distribute the data is completely up to us. So we can choose the data partitioning strategy. But let's say we give employee one's data to node one, employee two's data to node two. So what each of this node will do is it will process each of these rows, right? And produce a key value pair, right? And before going there, I missed one more thing. So let's say this meeting um, lasted for 1 hour. Per email, let's say this email conversation, we're talking about back and forth conversation, right? Let's say employees spend 10 minutes in this mail conversation, right? Say this meeting 2 hours, then employees spend 20 minutes in this meeting, right? So in node one, the uh, uh, the signal is processed one by one. For every signal, we are going to run map function, which is going to do this thing, right? So it's going to create this tuples, um, which is, it's going to flatten the data in the structure, saying, so even has collaborated with E2 for 1 hour, even has collaborated with E3 as well for 1 hour, right? This is just processing this signal. For mail, it will produce even has collaborated with E2 for 10 minutes. Even has collaborated with E4 for 10 minutes, right? The same thing is going to happen here as well. So here in this case, has collaborated with 2 hours. E2 has collaborated with E3 for 2 hours, and E2 has collaborated with E1 for 20 minutes. E2 has collaborated with E5 for 20 minutes. I hope this is clear. Let me know if you have any questions. Right. Okay. So this is what map function is going to do in each and every node, right? So if we go back to the slide, once the input data is given, the data will be partitioned, right? And we are going to define how we want to partition this data, and so that the data is distributed among all the nodes that's available, right? So we're going to partition the data and run map function on each of those data partitions. And then once this is given, ultimately our end goal is for any employee employee 1 to employee 2, right? We want to see their total collaboration, right? This is what we are interested in, right? So in order to produce this, now every map function has produced this, the intermediate data, right? Which is between any 2 employees, what is the collaboration, right? So that's the data we have as part of this map. That's the data that we have generated as part of this map function. But then the data is kind of distributed. This intermediate result is available in each and every node, right? In order to produce the total collaboration hours across any 2 employee, we need to aggregate this data, right? So what is done in this MapReduce framework? We have to collect all this data, right? Or we have to, yeah. Let's start with a simple thing, and then we can go into what this shuffle and sort does. So we need to basically collect all this data and reduce this data based on some key, right? So that means we need to do another function called reduce, right? And reduce by we have to choose a key to reduce. So let's use this key called employee ID, right? And here E1, E2, E3 are the employee ID. So we are going to run a reduce function based on employee ID. That means somebody is going to make sure that all the signal where an employee like employee 1 has generated, right, as part of their collaboration will reside on a single node, right? That means for employee 1, if you look at all these map functions, the output of these map functions, we have in this case, there's no data shuffle, right? So in this case, actually, let me put this way, right? All the signals where employee one is either on the left side or right side has to be present on a single node, right? Let's say that's the requirement. So that means we have four signals, or sorry, we have four signals where employee one is on the left hand side, that's produced by node one. In node two, there are two signals where employee one is on the right side, right? So that means we need to have all these six signals in a single node where we can run this reduce function, right? So let me, yeah. All right. So we are talking about these signals to be present on a single node. No, what this means is we need to shuffle this the intermediate data that is produced by these map functions such that um, we end up with the data that's where even has collaborated, right, in a single node. So this means we have to again, we are talking about shuffling very small amount of data in the specific example, but in real world we are talking about shuffling um, gigabytes of data, right, between this map stage and the reduce stage. So that's where the shuffle and sort stage comes into picture, where this stage is responsible for shuffling the data that's produced by map so that reduce function gets all the data in a single node where it can run the function, right, and ultimately produce the result. Now, this is for the specific example that I explained, this stage is unavoidable, right? And in fact, for most of the big data jobs, this stage is unavoidable unless uh, you you do some pre-processing, right? And even if you do pre-processing, you might still end up shuffling some amount of data, right, before you produce the final output. So, and in my own experience in building Viva Insights product, um, we spend a lot of time in this shuffle and sort stage as part of our big data job. And we have to spend a lot of time optimizing this stage so that our big data job process quickly, right? And I'll talk more about the optimization that we had to do to make the data processing quicker. But this is one of the big challenge that MapReduce as a paradigm introduced, and uh, we have to face this challenge, right, in a day-to-day basis. And the other problem this stage introduces is because we are shuffling lots of data across machines, network is not always reliable, right? So we had to face a lot of transient failures due to which when data gets transferred from one machine to another machine, either the bandwidth um, might be not good, or there could be broken network links, right? And this might result in the whole job failing, right? So you can imagine a scenario where you have run all this map functions across various machines, and you already spent several minutes or hours processing executing this map missions, and while you enter the shuffle and start stage, you encounter a network failure, right? Or the network is very slow, due to which things are timing out. So you are at the risk of losing all this intermediate results, right? Unless until you store this intermediate results somewhere. So these are all the challenges that we typically face when there's a lot of data that needs to be shuffled between the stages. Right. Any questions on this? I've explained a lot, but let me know if you have any questions.
In chat box, there is a question.
Oh,
You
okay.
have written data shuffles and are expensive. Is it with regards to the number of nodes or is it related to time? Even if we have a very huge file, if we have large number of nodes in our cluster, all map tasks can finish very quickly. Kindly elaborate.
Yeah. Thanks for uh, reading the question. So Ajay, data shuffles are expensive, um, and it is going to be proportional to the number of nodes in which you're going to run the map function, right? So, and it also depends on the amount of data that is shuffled across this node. So, um, so it is. So number of nodes is definitely a factor, um, and sometimes you have to bring in more nodes, right? Because to speed up the data processing. So that's also unavoidable. But what's in our control is the uh, the the partitioning strategy, right? So for example, if we can make sure that all the collaboration that an employee does is already pre-processed in such a way that they are all ingested to a particular node during the map execution, then we don't need a shuffle and sort, right? Because we already have all the data for an employee in a specific node, and we can do all the aggregations, all the computation on that node to produce the result for that employee. Right. Uh, and you have okay, you had two questions. Okay, okay, looks like I answered. Okay, great. Um, all right, so this is one of the challenge we face. Um, Now, the second challenge is um, I don't know whether you have noticed in my previous slide, um, between the map and reduce stage, we're introducing this stage called shuffle and sort, right? Of course, we discussed one of the challenge that the stage introduces, which is what we discussed so far. The other challenge is um, in order to do shuffle and sort, right? We have to first make sure that all the map functions are completed before you do shuffle and sort, right? So to give you an example, let's say, so in this case, there are four map functions, right, in the slide. Let's say this map function, the first map function took um, approximately 10 minutes to execute. The second map function also took approximately, let's say, 15 minutes. So the third map function took 20 minutes. This fourth map function, for some reason, took 2 hours to finish, right? So what that means is for you to run the shuffle and start stage, although all these map functions are executed within 10 to 15 minutes, you still need to wait for 2 hours in order to run the shuffle and sort, right? So we call this global synchronization barrier, map reduce barriers, right? In map reduce paradigm, that's what we call. So the problem is there could be strangler jobs, and you don't you there are multiple reasons why this job took 2 hours, right? Uh, One possibility is um, maybe this map function has given more data to process, right? That means there's something wrong with our data partitioning strategy. So we need to investigate that, right? What this means is data is not equally distributed across these map functions. So that's something we can control to a certain extent based on how we want to uh, 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 how we want to process the data, right? So we can optimize that, but sometimes it could be a problem with the machine where this map function is running. Maybe uh, the the CPU is faulty, or maybe there is some network issue when reading the data from blob storage in this map machine, right? Maybe this more network latency in reading the data. So there could be several reasons why this map function could be slow. But then the problem we will face is, since there is this global barrier that needs to wait for all the map missions to finish, map functions to finish, the uh, this will have a severe impact on the overall job execution time. Right? Basically, the shuffle and sort will start only after 2 hours, and then and the later stages will proceed after this. So this is another challenge we face, yeah, right? Specific to MapReduce paradigm, but this I would say is not specific to MapReduce paradigm, right? Any big data processing you do where you do distributed processing, and then there is a stage where you need to basically wait for all the previous stage tasks to finish before you start the next phase. That means you have effectively introduced the global synchronization barrier across all missions, and you're going to encounter this problem, right? Okay. Yeah. Yes, Ajay. I was just reading your question, your observation. Yeah, I mean, uh, map a map task can finish within a minute if the data that it's processing is under limit, and more importantly, what processing you are doing with this data, right? If you are uh, if you're running some image processing algorithm as part of the map task, it is going to take time, right? So it depends on what processing you are doing with the data. Cool. Yeah, thanks Ajay for making this session interactive. But I was hoping for more questions, more interactions. Um, uh, if that's not happening, then I would have to unfortunately assume that this session is not so interesting. But let me know if it's otherwise. Cool. All right. So the next challenge is job failures when the job is or when the data is getting processed. There are several stages. So in this slide we just talked about one MapReduce stage, right? But in a typical big data processing, there will be several repetition of this MapReduce stages, right? Before we produce the final output. So let's say you um, the job successfully processed all the stage except the last stage, and in the last stage it failed, right? So and the failure could be due to hardware crash, it could be due to network failure, or it could be due to some bug in your data processing code, right? Um, so now that means all the data processing we have done for several minutes or several hours is lost, right? That and what this means like to organizations like us, it's a huge waste of cost in doing this data processing, and these failures are inevitable, right? And these failures are bound to happen in distributed computing world. So we have to make sure that we don't lose the progress that we have made so far when processing the data, right? So that's an important factor to consider. Uh, and Yeah, so the next challenge is GDPR and other complaints that's without which we cannot run the business today, right? And see, I think the definition of all these complaints, GDPR is very lengthy. Uh, uh, but if I have to explain this with a one-liner, um, it's about giving control to user with respect to managing their data and what they want to do with their data. Right? At the end of the day, the data that we are processing is owned by customers, right? And we are just given the authority to process the data, right, and manage the data on behalf of customers. But if customer ask us to delete the data, we should provide that functionality, right? And if a customer asks us to um, um, limit the data that we should analyze, we should honor that, right? So that's what all this GDPR and other complaints is all about. And the other important factor is there are some regions, some geographies which mandates that data should not leave um, uh, their region, right? Especially when it comes to um, countries in Europe, they don't want the data that we process to leave the Europe boundary, right? So that means we have to honor that and make sure that we do all the processing in their own region of choice, and we need to protect the data from not leaving this boundary, right? Good. So these are all the challenges. Um, now I explained most of this without giving any concrete solutions, but in the next two slides, I'll discuss about some of the solutions that we have implemented um, to mitigate or solve this problem. Right. So some best practices. So before you run any big data job, right? Before you start implementing, you need to first identify the uh, the workload, right? And see whether it's uh, IO heavy or CPU heavy, right? For example, in Viva Insights product, um, we spend a lot of time in just reading and writing the data, um, um, compared to the time we spent on computing the metrics, right? Because most of the metric computation we do is simple computation, right? Simple aggregations. Well, there are some complex algorithms run, but ultimately, if you look at the actual computation we do after reading the data as part of all this graph algorithms, it's very simple, and we don't spend a lot of CPU cycles to compute this metrics. But then we spend a lot of time just reading the data, terabytes of data, right, as part of every big data job. So we need to first identify um, the workload um, that um that we have to handle and optimize the workload accordingly, right? So once you identify the workload uh, that you're going to process, the second thing that we typically do is we will identify appropriate data format in which you want to store your data, right? By understanding the read and access, write access patterns. Um, so to give in, there are popular formats that's widely used in big data world, like Parquet for column-wise access, Avro for row-wise access. So to give an example, um, let me. So let's say you have a table with um, with um, say this is one row which says um, okay, um, all right. So first row is about employee one, and employee one has spent this many hours in meeting. So there's a column which is going to say how many hours the employee spent on meetings. It's column two, which says how many hours employee spent in mails. Let's say two, right? E4, right? And this This basically continues, right? This is the data set we are going to process, right, as part of the big data job. So if ultimately, as part of the job, if the outcome is, hey, I want to aggregate all the meeting hours across all the employee, right? Total meeting hours. Similarly, I want to compute all the okay. Let's just take total meeting hours. So let's say this is the only metric I'm interested in computing, right? And this will have several other columns, right? I'm just giving an example, but let's say um, this table has hundreds of columns, right? And millions of rows or billions of rows, right? Um, so, but then we are only interested in computing this total meeting hours. So to compute this metric, I only need to read the value of this specific column, right? Which is meeting hours. I don't need to read each and every row or all the other columns, right? I just need to know the meeting hours of all the employees. So if you use column format like Parquet, and if you store your data set in Parquet format, Parquet internally stores your data set in a columnar format, right? That means if you have your data set in Parquet and if you use Parquet format to read, let's say, meeting hours, it doesn't read this entire table in order to read meeting hours. Rather, since the format stores this data set in a columnar format, it can quickly read all the meeting hours of all employees and return this, right? So now, if you use, let's say, CSV, which is a popular row based format, or even Avro, um, these are all row-based formats, right? And then there are definitely workloads which require row-wise data access as well. If that's the case, we can go with CSV or Avro. But for this particular workload, if you end up using CSV or Avro, then we end up reading this whole table, right? Which could be several millions of rows, and in terms of size, it could be several GBs of data, right? Uh, this is going to significantly impact the uh, your big data execution time. So it's very important to understand the read and write access pattern of your data set and use a data format that's optimal for your big data processing, right? And as Ajay mentioned, Parquet also has a very efficient compression technique, and this actually helps um, um, limit the network bandwidth that your big data job consumes when downloading the data, right? If the data is compressed effectively, then you're going to read less data, right? And that means you're going to use less network bandwidth, which is going to increase your performance. So that's one optimization. That's one thing that we definitely consider before we start implementing big data jobs, right? Um, the next one is, as I discussed, data shuffles are expensive for two reasons. One, you have to transfer lots of data between nodes, and um, then there's also this global synchronization barrier that I discussed. So you have to minimize. You cannot avoid altogether. It depends on your workload. Sometimes you can avoid, sometimes you cannot. But to the very least, you can try to minimize the amount of data shuffled across various stages using following techniques, right? The first thing is, we should always try to avoid shuffling the raw unaggregated data in the first stage of the job, right? The way we avoid in Viva Insights product is, we typically do some data, run a pre-processing job, that do one-time shuffle of this raw aggregated data to make sure that all the data that needs to be as part of a single shard is present in that shard, and we can run a map function on it, right? So we don't do shuffle of raw unaggregate data, right? And then once you've done this pre-processing as part of the first stage, the map stage, you have all the data in one shard. You run the map stage, you produce the output. But um, um, before you run a reduce stage, right, which might require the shuffle stage, you can try to do local aggregation of the data, right? That way you can limit the data that you need to shuffle across all the map stage, right? So that means you're no longer shuffling raw unaggregated data. Rather, you're shuffling an aggregated data, which typically would be less compared to raw unaggregated data, right? So that's something we try to do as much as possible to limit the amount of data shuffled across all the nodes. Now, how do we mitigate the effects of global stage barrier? I think we explained some of the mitigation strategies already. So one strategy we follow is we make sure the data is partitioned uniformly across all the nodes. Sometimes it's possible, sometimes it might not be possible. For example, let's say if you use something like employee ID as the partition key, there will always be a scenario where there could be some employees who collaborate a lot more than other employees, right? That means you might still end up having a partition which has a lot more data than other partitions, in which case you might have to consider splitting that specific user's data into multiple shards, right? Till a point where the data is evenly distributed across all the shards. So you have to think about, and of course, all of this also depends on the actual processing that you are doing. So you need to choose your partition key accordingly as well, right? But as much as possible, we should try to uniformly partition the data. But that alone is not good enough because, as I mentioned, there will always be nodes that might be processing data slower than other nodes, in which case we will see the effects of this global stage barrier. Um, so there are frameworks. Specifically, I mentioned one framework which is called timely data flow, which gives us the control to the user to decide when to introduce a global barrier, right? If you compare this to MapReduce framework, um, MapReduce stage always demands a global synchronization barrier, right? So in this case, even if the first three map finishes and those results can be consumed um, by the next stage, in this case, let's say reduce stage. MapReduce framework will not allow you. It will wait for all the map functions to finish before um, it starts the reduce phase. But with framework like this timely data flow, it gives us this control to user to define when to introduce global barrier and when to define not, so that you can, as part of the big data job you are implementing, you can say, okay, if a map function finishes, I can trigger the reduce function immediately for that map, um, for that output produced by that map, right? And I don't have to wait for all other maps to finish. So this control is given to the developer, and so that we can avoid the global synchronization barrier whenever there's no requirement. This is a very interesting framework. It's not widely used, but it's something we are experimenting with in Viva Insights product. And it has given us great results. So I would encourage you to go through this And there is a research paper published a long time back, and this framework is based on that research paper. So if you're interested, I would highly encourage you to go through this. I'll share the slides so that you have link to this framework, right? Cool. So the next thing is checkpointing the job progress frequently and resume from where it failed, right? And this is to mitigate the intermediate failure uh, uh, that we might encounter when running big data jobs, right? So as I said, any big data job we do, there'll be several stages um, um, that job needs to go through before it produces the final output. So you have to make sure that um, every stage progress and output is checkpointed such a way that even if there are failures, job can resume from that intermediate output, and it can resume, right? And popular frameworks like Spark um, has this capability, so it checkpoints and it tracks the stages, and if there are intermediate failures, it will automatically retry. So we can leverage that across the jobs. Of course, it's up to us to uh, um, make sure that your data is checkpointed, um, and uh, and you can resume from where it left, right? So that's something you need to consider when implementing big data jobs, especially series of big data jobs. So to the next thing is honoring GDPR and other complaints. So if you follow these best practices, one is irrespective of who's going to consume the data, we always put this data that we manage on behalf of customer behind a firewall or a network security group, so we call it, such that the data access is only allowed uh, to a specific region or a specific geography, uh, continent, depending on what these complaints mandate, right? So this way, even if someone tries to access the data outside uh, outside the geo where it's not allowed, data cannot be accessed. So you always need to um, uh, put the data behind a firewall, right? To honor these complaints, because if you violate, then it's a big risk of not being compliant, and the damage is severe, especially for companies like Microsoft. So it's very important to protect this, and it's very important to monitor the data access such a way if we detect any violation, we have to detect this in real time and raise this with the engineering team, right? Um, so this is all required. Um, the other thing that these complaints mandate is customer, as I said, customer is the owner of the data. So anytime they can say, hey, I want to uh, delete my data, right, for a specific employee or for a specific time period across all employees, right? Now, now we are talking about uh, even to process the delete request, right? Now we don't know which file or which folder contains this user's data, right? It could be across several thousands or millions of files. So in order to go and delete the data for a specific employee across these files, we will have to run another big data job. So to mitigate this, and we could get this request several times, right, across all the organization. So what we do is, as part of the raw data set, we don't actually store the real employee ID or employee name in the data set. Basically, we create a pseudo identifier in the data set that is actually getting processed. So we never go and persist the actual identifier of an employee in the data set. Rather, we have a separate map that's stored separately, which links the pseudo employee identifier to the real person, right? So this way, when an organization says, hey, I want to delete a person data, all we do is delete the entry in the map, which basically maps the pseudo identifier to the employee. So once that link is broken, with the pseudo identifier, nobody can actually identify the person, right? So the person has basically has gone anonymous in our data set. So this is how we handle this data delete requests optimally. This is all the optimizations that we do to handle complaints and complaints like GDPR.